It's Dr. Musk back again. So I'm here to introduce you to chapter 14, which is a catch-all chapter for a number of different functional groups. All right, so we're talking about functional groups that contain single bonds between carbon and a heteroatom. So specifically, an oxygen or a sulfur or a halogen. All right, and there are a few of these functional groups, so we'll have to go through them relatively quickly. We're going to focus the most on alcohols and a little bit on thiols as well. So alcohols we'll learn a couple reactions of, and the other functional groups we'll learn mostly just what they look like, some of their properties, and how to name them. So remember, alcohols contain an OH group. Now, we're not talking about things that contain an OH group next to a carbonyl. That would be something different, a carboxylic acid. So that is not an alcohol. This entire part of the molecule up here is a functional group. So we're talking about something that contains some sort of an alkyl chain connected to an OH group. All right, that's an alcohol. Ethers contain alkyl groups on both sides of an oxygen atom. So you guys can see the general structures of those on the left down here, and I also drew them because I wasn't paying attention to the bottom of the slide. And then some specific examples, a 2-carbon alcohol that we know as ethanol, so that's the alcohol that we drink in alcoholic beverages, and then diethyl ether, which is the most common ether that we use in chemistry. Next part of the introduction, we're going to talk about compounds that have a single bond between carbon and a halogen. We call them alkyl halides. So you can see the general structures of those are just some sort of an alkyl group bound to a carbon. So we could have something like this, which we would call iodocyclohexane. But there are tons and tons of examples. So any kind of alkyl group that you can think of, cyclic or acyclic, could be an alkyl halide. Also, if you have an alkyl group attached to an SH, those are known as thiols. So small molecular weight thiols are super smelly, all right? They are some of the smelliest compounds known. For example, skunk stink is primarily made of butane thiol. Small amounts of thiols are also used to make natural gas that is captured for burning for power. They actually flavor it with a little bit of a thiol that makes it stink, or else we wouldn't be able to detect the smell of natural gas at all. So regular natural gas doesn't stink. We dose it with a little bit of a thiol so that the human nose can detect where there's a gas leak, all right? Or otherwise it'd be a huge safety concern. So here are some examples of compounds that contain each of those functional groups. So it turns out that a slightly larger thiol, one with another heteroatom in it, is responsible for the smell of coffee. That's not particularly bad smell, but ones that are just small alkyl groups like ethane thiol or butane thiol are super stinky. All right. You can see next door there is both an ether and an alkyl halide. All right. So most of the hydrogen atoms that would be in that ether have been replaced with either fluorines or chlorines. So those tend to be called perfluoro ethers, and they're very common in the world of anesthesia now. So they're safer anesthetics than just diethyl ether, for example. And then a much larger compound that is both an alcohol and an ether. You can see the red atoms there. That's Taxol, an anti-cancer compound. So let's begin our discussion of the structure and properties of just alcohols first. All right. So alcohols contain an OH group, just like we said. And for some reason, this hasn't rendered very well. A primary alcohol, so that should be 1' there. All right, the degree sign after the 1. A primary alcohol has only one alkyl group on the carbon bound to the OH. So that one alkyl group there is what makes this a primary alcohol. If the carbon that is bound to the OH, this carbon right here, is bound to 2 alkyl groups, then we call this a secondary alcohol. And if that carbon bound to the OH group is bound to 3 alkyl groups, we call it a tertiary alcohol. So alcohols contain an oxygen atom that has 4 electron groups. 2 of those electron groups are lone pairs. We know things with 4 electron groups have a bond angle of 109.5 degrees. And because of those 2 lone pairs, we give the shape around oxygen in all alcohols the designation of being bent. That's the correct shape. So because alcohols have 2 polar bonds, they tend to have net dipoles, all right? So pretty much always. So if we draw in those bond dipoles on methanol here, we can see that they both point up toward that oxygen colored in red, which means the oxygen's the slightly negative side of this molecule, and the side with the carbon and hydrogen is the slightly positive side of this molecule. So methanol, just like pretty much all alcohols, are polar, all right? Those dipoles point toward the oxygen side of the molecule. So because alcohols have a hydrogen covalently bound to oxygen, they're also capable of forming the strongest type of intermolecular forces. So that's when a very delta positive hydrogen, and it's very delta positive because it has a covalent bond. I put an arrow into that covalent bond. That covalent bond to oxygen, a very electronegative atom, gives this delta positive hydrogen here some sort of superhero properties. Because it's so very positive, it can form an especially strong attraction to a delta negative oxygen or nitrogen or fluorine on another molecule. And that very strong attraction is called a hydrogen bond. It's not really a covalent bond. It's an attraction between molecules, but it's the strongest type of intermolecular force, all right? So what does that mean about alcohols that they can hydrogen bond? Why is that important? Because that's the strongest type of intermolecular forces that covalent molecules can have, that means that alcohols have much higher boiling points and melting points than hydrocarbons that are the same molar mass. So if we look at butane, which is approximately the same molar mass as 1-propanol, you can see that the melting point of butane should actually be negative 138 degrees Celsius, and its boiling point 0.5 degrees Celsius. The melting point of propanol, that doesn't make sense at all. The melting point of propanol should be slightly lower than room temperature, but that boiling point I think is correct, 97 degrees Celsius. So the key here is that as our type of intermolecular forces gets weaker, the boiling point and melting point get lower. And as the type of intermolecular forces get stronger, the melting and boiling points get stronger. All right, they get higher. So because alcohols are polar, low molecular weight alcohols end up being very, very much like water. They're very polar, so they tend to be soluble in water. All right. Now, larger alcohols, because they have more carbons, they become more hydrocarbon-like, and they're not as soluble in water anymore. So a small alcohol like ethanol is water-soluble. A big alcohol like octanol is not soluble in water. And pretty much all alcohols are soluble in organic solvents, all right? So they're not nearly as polar as water, but the small ones are polar enough to dissolve in water. That's probably a long enough video for the start, so when you're ready, go ahead and tune back in, and we'll start discussion of section 14.3. Thank you guys for paying attention. This is Dr. Musk.